Hi, welcome back to episode 1 in our new Radio Design 401 series. This is part 2. And if you've already seen part 1, you know that what we're talking about is low power receivers in crowded spectrum environments. What does that mean? Well, it means when radios are trying to pull out very weak signals in the presence of very strong signals that are all grouped tightly together, such as in the FM broadcast band, which is what we see here. And in part 1, and also in epilogue 3 of the prerequisite Radio Design 101 series, we looked at the performance of several different radios, including some of the newer ones. And what we found was those radios struggled with some signals that were present in the environment, but they just could not receive them. So today, in part 2, we're going to talk about why and what you can do about it. In particular, we are going to be focusing on what's called the intermodulation problem. That is a fundamental problem that can occur in any radio design. But in part 1, we illustrated it using this little radio. So I'm going to play that again here real quick.
In a tight job market with plans to consider adoption on first reading at their April 19th meeting.
So what we just heard are these two stations, 96.3 and 93.3, even though the radio was tuned to 90.3. We didn't hear 90.3 at all. And that's, of course, because 90.3 is very weak. But why did we hear these two stations? Well, that's what we're going to be talking about. Here's the origin of the problem. We've got a radio receiver with an antenna. And what's coming into that antenna is the signal we want, and interferers, all those other stations that we don't want, as well as background thermal noise. And it's the job of the radio receiver's processing circuits to pull out that very weak signal in the midst of all this other stuff. Well, there are many ways for that to go wrong, but we're going to talk about two of the more fundamental ones here in this slide. One is what's called the blocking problem, and then we'll get to that intermod problem. The blocking problem is, in a sense, the simpler one. In this case, we have an antenna and we go through what's called a pre-select filter, and then we go into a so-called low noise amplifier, and then it flows on to the rest of the radio, such as the mixer for down conversion and the IF filter for channel selection. The problem is this so-called pre-select filter typically lets through the entire service band, all the signals. Here, I'm just going to have two. One is a very weak signal that we're trying to receive, and one is a very strong signal. And that strong signal I call the interferer, and it is at minus 10 dBm. That's 0.1 milliwatts, so that's a very strong signal coming in. Meanwhile, the weak signal is 100 dB lower in signal strength. So this is a challenging problem, right? So down in the lower left corner, this is a spectrum plot, like you might see on a tiny spectrum analyzer, for example. If it was working perfectly, you would see the strong interferer signal at minus 10 dBm at its frequency called F1, and you would see the weak signal at frequency F0 at minus 110 dBm. And there would be some noise floor as well, where you can't see anything below that because, remember, in addition to the signals coming in, there is noise. To the right is a spectrum plot at the output of the low noise amplifier. Remember, both of these signals are within the passband of this filter, so they both got through. So this represents the plot before and after the filter. But at the output of the amplifier, things are interesting. The amplifier's gain is listed as 30 dB. So our minus 110 dBm signal should have gone up to what? Minus 80 dBm. That would be here. But it didn't. And why is that? Well, let's look at the interferer. The interferer started out at minus 10 at the input to the amplifier, and it should go up 30, so it should be plus 20 dBm at the output, right? Except that in the real world, well, what's plus 20 dBm? That's 100 milliwatts. And this is assumed to be a low power receiver with a low power LNA. And we're assuming here it's 5 milliwatts, for example. Well, you're not going to get 100 milliwatts out if the LNA only draws 5 milliwatts. Also, it's only about 20% efficient, so at most we get out maybe 1 milliwatt. So that's shown here as the actual output power for the F1 signal at 0 dBm. So what about our desired signal at frequency F0 here? Well, it should have gone up, but it didn't. And why is that? That's because we have something called gain compression. This amplifier doesn't have the gain it was supposed to have because we hit it with too strong a signal. And finally, this amplifier generates some of its own noise. There's not just noise coming into the antenna. All electronics generates their own thermal noise, and so that's coming out at about minus 93 dBm. I'm not going to go into the details on that, but the point is the actual output power that we get from the desired signal is now below the noise floor, and we're just not going to hear it. So that's what we're saying right here. The solutions are, well, you could have a 1 watt amplifier here, for example. So use a higher power LNA. But that doesn't work if you're trying to design a low power receiver. The other thing you could do is decrease the LNA gain. Don't make it 30 dB. It sounds great because it's a big number, but we've just learned that it's not a good idea. So in practical receivers, we usually limit the gain here to maybe 10, 15, 20 dB. Still going to be a problem in this case, though. So what would be much better is if we could filter out this interferer before it got to the low noise amplifier, which means narrow up the preselect filter so it doesn't get through to the amplifier. And we're going to show how to do that. This is a slide from part 1, but it was also in epilogue 3 of Radio Design 101. We're going to see how this circuit can generate a transfer function, this blue line, which actually attenuates out-of-band signals before they get to this amplifier. But let's come back to the Intermod problem that was causing the issue in this demonstration. The reason we're going to focus on that is because this problem occurs at much lower signal levels of the interferers than the blocking problem typically. So we're sticking with our same block diagram as we just looked at for the compression problem, and the same desired signal level, minus 110 dBm, but now the interferers, instead of minus 10 dBm, are 30 dB less. They're minus 40 dBm coming in. Those aren't very strong signals. So in the lower left, this is what our spectrum looks like, coming into the filter and coming out, because we haven't narrowed the filter up. This is a traditional design in this slide. We left the gain of our amplifier at 30 dB, and let's see what happens. The minus 40 dBm interferers should go to minus 10 dBm. Okay, it's a 5 milliwatt, 20% efficient low noise amplifier, so it should be able to output signals at 0 dBm, so these are not compressed. However, a new problem rears its ugly head because there are 2 or more, but usually we just look at 2 at a time, just makes the discussion easier. So there are 2 interferers at minus 10 dBm. They are at frequencies F1 and F2. And meanwhile, our desired signal is at frequency F0. But now, at the output of the low noise amplifier, we have 2 more signals, and we call them Intermod products. One is here, and it's labeled minus 70 dBm. There's another one up here. And what frequencies are those at? Well, if this was a university course, then we would have spent a couple of lectures already discussing how those got generated and all the mathematics and so forth. But I'm just trying to give you the overview here. We'll get into more math later in this Radio Design 401 course. But to cut to the chase, the frequencies are listed here. 2 times F2 minus F1. So to make this concrete, let's assume that F2 is 100 megahertz and F1 is 99 megahertz. Those numbers just make it easy to calculate. So 2 times 100 megahertz is 200 megahertz, subtract off 99 megahertz, and you end up at 101 megahertz. So that's right here. So there's 1 megahertz between here and here, and between here and here, and between here and here. The intermod that falls on F0, what would that be? Well, that's 2 times F1 minus F2. F1 is 99, so 2 times 99 is 198. Minus F2, that's 100. So 198 minus 100, that's 98. So this is 98 megahertz, and that's the assumed signal that we're trying to get. And depending on how strong these signals are, and the amplifier design and how much power it consumes and burns and so forth, those Intermod products can be bigger than the desired signal, and you won't hear the desired signal. You'll just hear the Intermod products. And that's what we heard when we listened to this little demo.
In a tight job market, with plans to consider adoption on first.
But the desired signal we will not hear because it's weaker. So what can we do? Well, same as before. You can use a higher power low noise amplifier, burn more power, but we can't because we're trying to design low power receivers. You could decrease the LNA gain. That's probably a good idea. Or you could filter out F1 and F2 before they get to the amplifier. And again, that's what we're talking about here today, filter design that can do that. Design of filters to act as a pre-select filter that are so narrow that they can block out F1 and F2, or at least attenuate them to the point that they don't produce a strong enough intermod to interfere. Now, this is the first episode in Radio Design 401, which is an advanced course. So what that means is I'm going to assume that you have some experience with the circuit designs that we'll talk about. You may have covered those in school, or you may have watched Radio Design 101 series, which I labeled as our prerequisite here. It was built around a university course. And in that course, we covered all the material that's needed to design, build, test, and use an FM broadcast band receiver. What we did not do was look at how well it performed at the end. That we did in a couple, 2-3 epilogues in the series. And the subject of how to fix the issues that we found in those epilogues is the subject of Radio Design 401. We're going to be looking at this intermodulation problem in depth and the solutions to it. But since this is an advanced course and also a sort of white paper on research, we're going to look at basic research in low power receivers. But a lot of our focus will be on circuit level solutions. So let's now drill down from this slide, which is at a block diagram level, to the circuits that make radios possible, that make the block diagram possible. And the material will be general. We're just going to use the one that we did in Radio Design 101 as a starting point, and show how the blocking problem, in particular the compression problem, and how intermods arise. And let's do that using a circuit simulator, something that we could all do if we have a pretty decent personal computer. I drew this schematic and ran this simulation with a program called LT-Spice. LT-Spice. And the circuit here is a common base amplifier, Q1, followed by a common drain buffer, Q2, to the output, VO. The input is here, VI, and the source signal is over on the left. It's currently configured at 98 megahertz, and 0.05 is the amplitude. Now I gotta make a comment here. It says 25 millivolt peak. This is actually the peak value of this sine wave source is 0.05. However, it is assumed that you would be driving into a 50 ohm load at this point. This right here is a Thevenin model of a signal generator on an RF test bench. And it's assumed when they show you the signal level that you're connected to a 50 ohm load. So the voltage that you put here has to be twice what you want it to be coming into the circuit. So it's a 25 millivolt signal that I punched in on the signal generator, and I'm modeling that thusly. Okay, very quickly, 50 ohm source, and then we go through a DC blocking capacitor, This is just basically almost 0 ohms reactance to 100 megahertz. And then it goes into the amplifier, comes in on the emitter. The base is grounded, AC grounded, so it's a common base amplifier. And the output of Q1 goes to this LC tank circuit. And R2 is the collector load resistor, and it's picked to give a voltage gain of about 10, which in dB domain is 20 dB. And then that goes into this buffer, and what's the gain of that? Well, it's unloaded pretty much, and so this is a voltage gain of about 1 from the base to the emitter, which is the output. This stage is rebiased with R11 and R10 to provide the ability to have as big a swing as possible here at the collector. So let's look at those signal swings. The output is in red, and the peak-to-peak amplitude is about 1.85 minus 1.35. That's about 0.5 volt peak-to-peak signal swing. Assuming the input at VM here really is 25 millivolts, let's see, what does that mean? Well, 0.5 peak-to-peak is 0.25 peak, and so that's a gain of about 10. All right, good. But what about VI? Is it really 25 millivolts? Well, you can look at the blue curve here and ascertain that for yourself, and I would argue it's pretty darn close to it. Good enough. All right, let's see what happens when we go to a 100 millivolt peak-to-peak input signal. That's 4 times larger, and so the output should be 4 times larger. And let's see if it is. Well, to keep this video from getting too long, I'm going to let you freeze this here and do your own computations and see if you agree that the voltage gain in this case ends up being only 8. So we have actually decreased our voltage gain. That's because the output is in compression, like we've been talking about. It's about 2 dB compression because we now have 18 dB gain instead of 20. But now we can talk about why that is. So the curve above the output voltage graph is the collector current graph. And this is really, really important to look at this. People do not talk about this stuff enough. They just say, oh, you've got non-linearities in the transistor, and so you get compression and intermods and stuff. But where are those non-linearities occurring? Well, they're occurring, in this case, in Q1, and they're occurring mainly in the collector current graph. They don't show up very clearly in the output voltage graph. Why is that? Well, we've got a LC tuned circuit here. So it will take this waveform and filter out all but the fundamental and leave a beautiful sine wave. But here's what's really happening. This collector current waveform looks pretty bad. And the reason is this input voltage is varying the base to emitter voltage. The base is held constant with this bypass capacitor, but the input signal is coming in on the emitter. So the base emitter voltage in this transistor is varying. Of course, that's what makes an amplifier work. That changes the collector current, but it's varying too much. And we can see that by looking at this slide from the Radio Design 101 series on RF amplifiers. This is from episode 3 of Radio Design 101. Over on the left is just a basic transistor, and we've got the base emitter voltage here, and we vary it. And so that's on this axis, base emitter voltage. That changes the collector current, assuming we've got the collector pulled up with a decent voltage, and that can be seen on the vertical axis, I sub C. Notice that this graph is, well, it's supposed to be exponential. I couldn't draw a perfect exponential, but you get the point that it's not a straight line. So as we vary the base emitter voltage, we move along this curve. And if we go too low with the base emitter voltage, we get into a gentler slope, and that means the transconductance goes down. And that means the gain goes down. And we can see that happening on the positive peak of the input voltage VI. At the positive peak, that means that there's less voltage from the base to the emitter, because we raise the emitter. So VB minus VE is a smaller value, which means the current is smaller, and we see it happening here. So that's what's causing the compression. But remember, the intermod problem can occur at much weaker interferer levels than this problem. So let's move on to the intermods. Here's a simulation of that. And again, I highly encourage you to get your own favorite simulator, or you could download LT Spice, it's a freeware thing, and run the simulation yourself. If you do use LT Spice, you could just put a regular NPN transistor here. This one I had to find a model for it and put it in the library, so that's kind of a pain. But just sticking a regular NPN transistor here would be fine. So I'll try to run through this pretty quick, and you could always freeze the frame here and come back to it if you want to study it in more detail. But let's go quick here. First of all, the input signals, there's now 3. There's 2 interferers and 1 signal. The signal, you probably can't read it, but it says 2 times 10 to the minus 6 volts. So that's 1 times 10, that's 1 microvolt. So it says 1 microvolt signal here. Remember, whatever you have here gets divided by 2 because it's assumed the source is going into a 50 ohm load. That's at 98 megahertz, like in the example I gave you before. The interferers are at 99 and 100 megahertz. And they are 0.05 volts, which means they're 25 millivolt interferers coming into the amplifier. Now, this simulation is a bit involved. We still plot the output voltage and the input voltage in red and blue respectively, and the current in gray. But they look really weird, and that's because I have to run them for hundreds and hundreds of cycles. Actually, I ran it for 10 microseconds of simulation time. And that's because we're going to do a fast Fourier transform on the result and plot the result from 88 megahertz to 108 megahertz. And when we do that, what do we get? Well, this is VO. It's the output voltage here. And we see the 2 interferers. We do not see the desired input signal because it's 1 microvolt and it is just covered up by this intermod right here. So these are the 2 intermods that we talked about in the previous slide. What are these? These are what are called 5th order, 7th order, and 9th order intermod products. We're usually only interested in the first 2 that flank the interferers. Now let's look at the next case where we keep the signal level at 1 microvolt, but we drop the interferers by 20 dB from 25 millivolt to 2.5 millivolt. Incidentally, 1 microvolt signal level is about minus 110 dBm, so comparable to what I showed you in the block diagram. The 25 millivolt peak interferers come out to about minus 20 dBm, it's minus 21, minus 22, but about minus 20. But now we're going to drop them to about minus 40. When we do that, they are lower in level at the output than they were before. That's no surprise. We dropped them by 20 dB, a factor of 10. So they dropped from, what is this, 0.1 volt, about 0.2 volts down to 0.02 volts. Okay, that's expected. Exactly right. The intermod products, the 3rd order intermod products that flank them are here and here. Oh, and what's this? That's our signal. That's our signal. So when the interferers are weaker, the intermod products are weaker, but they're a whole lot weaker. We dropped this by 10 dB from the previous case, but these guys fell by 60 dB. And when we do cover the math in future episodes, we'll see why that is from the math. But the take-home is, remember, intermods drop very quickly when the interfering signal levels are weaker. So that actually brings up a really good solution, and one that's incorporated into many different radios. If you're an amateur radio operator, you may know, for example, that if you turn on an attenuator in your receiver, you can sometimes hear stations you could not hear before. So I didn't draw it on this block diagram, but you could put an attenuator right here or right here, and that would decrease the interferers coming into the amplifier. That sounds great. Okay, so let's just do that. Oh, wait, this signal is at minus 110 dBm. If we drop it by 20 dB with an attenuator here, it'll be at minus 130 dBm, and that's actually weaker than the noise floor. So that's not going to work. So we need a better solution. That's what we're talking about today. So here is our better solution. Reduce the front end bandwidth to the signal bandwidth, not just the width of the service band like virtually all radios do today. If we could somehow design a filter here that is extremely sharp, very narrow band that is, then we could block out the interferers before they hit the low noise amplifier. It's as simple as that in principle. Doing it in circuits, it's a challenge. So before we go to our circuit designs and the prototypes that we've built and tested, let's look at this graph and figure out what it's talking about here. This red curve is the frequency response to the output of the low noise amplifier / image filter. Now, as we saw previously, there's also some pre-selection filtering going on, but let's just look at this red curve right now. It's pretty narrow. This is 90 megahertz, this is 89, so it's about 200 kilohertz-ish wide, and that's the channel width for FM broadcast. These little arrows mean that it's adjustable, so we can adjust, for example, the gain here, and that moves the red curve up and down, and we can adjust the frequency of these filters left and right. We can also adjust the bandwidth. Let's see how we do that in practice. So let's start with our first prototype. Good place to start, right? This was actually shown in Epilogue 3 of the Radio Design 101 series. And it's an amplifier pretty much like the one that we just talked about. This is a common base stage, and this is a common collector or emitter-follower buffer stage. The common base stage doesn't have a bypass cap here because when I was doing this, I was lazy and I knew that this was already AC ground up here, so I could get it biased upright as well as provide an AC ground by just tying it to the VCC node, V2. But other than that, it's pretty similar to what we just looked at. There are a couple differences. There's a tunable capacitor here to change the frequency. And there is this, which is what's called positive feedback. One other thing, I've implemented a 500 ohm source resistance over here on the left. That could be done with a 50 ohm source by building a little matching network here, like we talked about in Radio Design 101. Let's look at the frequency response. So the response to the output node is shown in the red curve. This curve right here is just phase, so ignore that. So the amplitude or the magnitude in dB of the voltage gain is here in the red curve. Now, it says VO is 30 dB, so why am I calling that the voltage gain? Well, if we come over here and we look at the AC source, it has a magnitude of 2. But remember, it gets divided by 2 if you have a matched input impedance, and so that's really 1. And so if the input is 1, then the output voltage is identically equal to the gain. It's a little trick you can play to more easily simulate gains. Now let's examine this graph more detail. It looks like it's centered at about 98 megahertz. Okay, that's kind of what we wanted. And it has a 30 dB gain, which is a lot, as we've learned, but notice that it drops off very, very quickly. So we would say that it has a very narrow bandwidth. Now, in Radio Design 101, we learned that bandwidth is related to something called Q, or quality factor. And here's a slide from that Radio Design 101. This is actually from episode 1 of Radio Design 101. And we talked about the circuit Q. For a parallel tank circuit, which is what we have, the Q, the number, is equal to the resistor divided by the reactance of either this or this element. They're both the same at the resonant frequency, so I just called it XO, the reactance, at the center frequency, F0. The bandwidth is then found, as you probably remember from your school or from Radio Design 101, as the center frequency divided by the Q. So for this filter, what is it? Well, if we look at the values here and we crunch the numbers, I got a Q of about 13, which this was a reactance of 75 ohms, and this is 1K. I'll assume the input impedance here is very high, so I'll just use the 1K. And so that's a Q of 13. We're at 100 megahertz or thereabouts, and so that's a bandwidth of about 8 megahertz. That is a lot wider than what we're seeing here. Why is that? Well, that's because this is a so-called Q-enhanced filter. So the positive feedback, which is this line up here that comes back to the input, that positive feedback does two things. It raises the overall gain, so that's how we got 30 dB out of this thing, and it narrows up the bandwidth. It also has an effect on the input impedance of this amplifier. Now, this thing was designed to have about a 50 ohm input impedance, but if you trace this line back, you see there's a 50 ohm resistor to ground here, so that means the net impedance looking into this thing is about 25 ohms. Ooh, we got 500 ohms driving into 25 ohms. That's going to create a huge attenuation. That sounds bad, but it's actually very, very good. That's what yields this blue curve here. This is the gain from the source to the input node voltage. And outside the passband of the filter, we get hit with a 20-ish dB attenuation. That's due to that voltage division we just talked about. However, the input impedance of the filter goes up at the center frequency, and so we actually get a gain at the input of about 2 or 3 dB. So that basically means that the input impedance looking in here is actually higher than 500 ohms in this case. But the most important thing is that only happens at the center frequency. At other frequencies, we do get attenuation due to the voltage division of 500 ohms looking into 25. And what's that good for? Well, that's good for decreasing signals outside the passband, which is what we want to do. That essentially gives us a pre-selection filter function before the input to the LNA. So we get to reduce the interferer signal levels before they hit the LNA and generate these nasty intermods. That's what we're trying to do. Now, in later episodes, we will cover the design of this filter and how that feedback does that. However, let's look at the actual prototype where we just built it up and tried it out. So this is shown here. This is the very first prototype. It's built on a proto board that we used in Radio Design 101. Now you can pause the video here and try to match this up with the circuit down below. I'll tell you a couple things, but I don't want to spend too much time on it right now. Q3 is this transistor right here. The emitter is here, the base is here, and the collector goes over here. And the collector is tied up to VCC, 5 volts, right up here along this line through this inductor. This inductor is big. That's to make the starting Q of it pretty decent. Remember, we're starting with a Q of about 13, but that's only going to be the case if the quality factor of the inductor itself is much bigger than 13. So this guy has a quality factor of about 100 at our center frequency, so it's not going to effectively lower the Q of the whole tank circuit. The Q is determined by R2, as we mentioned earlier. The feedback is controlled with this potentiometer, this blue guy right here. It comes from the output and then is fed back, hitting a 51 ohm resistor along the way. That's this guy here, R5, and then going through a capacitor back to the input, which is here. This R6 is actually the source, but we have a 50 ohm source and we're looking through a LC matching network. Here's the L, it's 220 nanohenries, and the C is, let's see, I think it's this one, which is, I believe, 7 picofarads to ground. So this node right here is ground. The other thing I should mention is this is not a mechanically variable capacitor. I'm actually using a varactor diode here, and that's this guy. And it's controlled with a potentiometer up here that controls a DC voltage on it. And the output buffer is here. Base, collector tied to VCC, and emitter going out. In this case, through a 100 ohm resistor that gives about a 10 dB attenuation on the way out. That's just because we have a 30 dB gain and I didn't want that much before the radio that I fed this signal into out here at the output. Now, does it work? Yes, it works very, very well. This top plot is the spectrum at the output observed on a tiny spectrum analyzer when the filter is tuned to 96.3, which is the super strong station in our area. But I backed off the Q enhancement with this potentiometer to minimum, and also remember there's attenuation here on the output. In any case, the signal there at 96.3, it's already strong. I don't need to amplify it. So there, it's fine. And the interferers are out here and they're all weaker. That's no problem. What is a problem is trying to receive these signals down here in the lower end of the band. Notice they're essentially right at the noise floor. But if we retune the center frequency using our varactor diode with this potentiometer, and we increase the positive feedback by cranking up this guy, which actually cranks down this resistance, then we get that peaking here. And we can get like a gain of 30 dB, but only at that low end frequency. Now, here it's shown at 98 megahertz, but I've moved it down to the bottom. So it's closer to this case. Now, note that 96 megahertz is over here, and the gain from the input to 96 megahertz is now negative 3 dB, or something in that region. And at the same time, I have close to 30 dB of gain at the low end of the dial, which is where I want it. So the result is this. We've taken these signals and raised them up, and at the same time, this strong signal is actually decreased. So yeah, this one's a little stronger, and these are about equal, but that's not going to produce enough intermod issues to cause us a problem. So we can now receive these stations. Pretty cool. And from part 1 of this episode, you may recall that all the other radios that we tried without this filter could not receive a signal at 88.1, which was close to the noise floor. Even the fancy new radio that we have could not get it well. However, our simple little radio that we designed and built in Radio Design 101, with the addition of this filter, this is a later version of it that was done on a PC board, with this filter, we can actually receive that station when all of the others could not. So let's take a quick listen to that, and you'll see the test setup that I've got here. I'm using the filter to augment the behavior of this really not very good receiving radio here that could not get that signal at all, but you'll hear that it can. Here it is in this spectrum analyzer plot. It's down at the noise floor. So this is 88.1 FM. This is at the very bottom of the dial. It's one of the weakest stations here. This radio normally has massive problems, but we have the filter in front of it and it is working good. It's that station there on the lower left. So this thing really works, and this is even without optimizing it. We've done a little bit of design work in here to get it to work as well as possible, but not a great deal. So this is kind of a proposed filter design. It's a filter that allows us to make low power receivers that work in crowded spectrum environments. And this is not something that's really done these days. These filters are, I don't know, I don't want to use this term, but they're kind of cutting edge. And so remember, this is, in addition to an advanced course, Radio Design 401, this episode is essentially a white paper. This is a proposed way of doing stuff in the future. Now, there are other ways of dealing with crowded spectrum environments. If you're a radio amateur operator, for example, you may have a beam antenna that you use during field day, and it can really point in a certain direction and somewhat reduce signals that are coming from different directions. So that's another way to do it. Another way to do it is to use a resonant loop antenna. And this is one that I put together, I don't know, several months ago in episode 9 of the Antenna Briefs series. And here I'm using the small loop together with the Q-enhanced filter because I thought, hey, let's put the two together, see what happens. So you can look at that episode if you like. I'll come back to this diagram here, which is our later prototype of the Q-enhanced filter. So those are really the punchlines from this part 2 of episode 1. However, okay, enough of that. Why does this research matter? Well, obviously it matters because it will allow us to receive more stations. That's pretty clear. But why does that matter? Well, spectrums have become more crowded, and we always need more efficient use of spectrum resources because we've got Internet of Things, we've got cell phones, we've got Wi-Fi, et cetera, and sometimes they're in crowded environments like a apartment building or an office building or something. So spectrums can get very crowded. Turns out that the regulatory agencies, the International Telecommunications Union internationally, and the Federal Communications Commission in the United States, and NTIA also, they are starting to care about receiver performance because it's being recognized that this intermod problem, these problems we're talking about, are what's controlling how well you can use spectrum resources. And if you want to know more about that, here is a FCC fact sheet from 2023. So this is happening today. It's happening very, very slowly. But what they're doing is they're starting to try to promote a balanced and comprehensive approach to spectrum management that holistically considers both the transmitter and receiver components of wireless systems. So we care about receivers now, not just transmitters and their spurious emissions. And that brings us to the end of part 2 of episode 1. Thank you for watching, and hopefully I will get part 3 out before too long. Thanks again.